Hello, in this video I'm going to be solving two exercises from section 2.4 of Jiří Lebel's notes on Diffy Qs. So both of these problems are on linear independence of functions, or dependence. And for the first problem, we're given the functions e to the x minus cosine x, e to the x plus cosine x, and cosine of x. And we need to determine if these three functions are linearly independent or not. Similarly, for exercise 2.3.9, here we're given x, x squared, and x to the fourth. And again, we're asked to show if they're linearly independent or not, giving an example of a linear combination if they are not. Okay, so let's start with 2.3.7. So first, let me recall actually the definition of linear independence for three or more functions. So we say that f, g, and h are linearly independent if the only way for C1 f of x plus C2 g of x plus C3 h of x equals 0 to hold for all x, and this is important, for all x, is if the coefficients C1, C2, and C3 were all actually 0 at the onset. Meaning that we can't have like C1 be 2, and then like C2 be like 1, and C3 be -3, and have this identity hold, where this is equal to 0 for all x. This is saying that the only way for this to happen is if all of the coefficients themselves were 0 to begin with. And so, if we're going to see whether these three functions are linearly independent or not, we first write C1 f of x plus C2 g of x plus C3 h of x equals 0. And we're going to try to see if we can figure out what these coefficients have to be. Okay. Now, one thing we can do, and this is kind of general, this is pretty general, it can be applied to many classes of functions, is we can use differentiation. Now, to illustrate what I mean by that, first, the goal ultimately for us is going to be to get at least three equations, and I'll write this in blue. Our goal is going to get three different equations relating C1, C2, and C3. And one way to do this, and I'll write this in another line, is to plug in different values for x. And let me illustrate what I mean by this. So here, just given that f of x is e to the x minus cosine x, this is e to the x plus cosine x, and this is just cosine x, we can see that if we plug in 0 for x in all three of these, we're going to get the equation. So first, let's compute what f, g, and h are all at 0. So f at 0, by what I just calculated, is 0. G of 0 is e to the 0 plus cosine 0, which is 1 plus 1, which is equal to 2. And h of 0 is just the cosine of 0, which is 1. we see that plugging in 1, or x equals 1 for that matter, into, and I'm going to call this equation star, into star gives that, okay, well, f of 0, when we plug in x equals 0, is going to vanish, so c1 vanishes. And then we're going to have c2 times g of 0, which is 2. And you know what? I'll add in the c1 part just for completeness. And then the c3 part is just going to be 1 when we plug in x, and this is 0. And this says the same thing as 2c2 plus c3 is equal to 0. Nice. Now, another thing we can try, maybe there's another x value we can plug in. But here, the problem is that if we plug in anything other than x is equal to 0 into these functions, we're not necessarily going to get nice values per se. And so instead what I'm going to do is I'm going to differentiate the equation star. So I get c1 f prime of x plus c2 g prime of x plus c3 h prime of x equals 0. And so now, if we play the same game of plugging in values for x, well, what are the derivatives? Well, f prime of x is going to be e to the x plus sine of x. G prime of x is going to be e to the x minus sine of x. And h prime of x is going to be negative sine of x. And so if we plug in x equals 0 into these, well, if we plug in 0 here, we're going to get 1 plus 0, so we get 1. You get 1 minus 0, so we get 1, and then we get 0. So this is c1, 1, plus c2, 1, plus c3, 0 equals 0. And this says the same thing as c1 plus c2 is all equal to 0. So that's the second equation. Let's get one more. Again, we have 3 unknowns we're trying to solve for, so it makes sense to get 3 equations. And so for this, I'm going to differentiate once more. And so now I get c1 f double prime of x plus c2 g double prime of x plus c3 h double prime of x equals 0. And now computing the second derivatives, I'm going to get e to the x plus cosine x. G double prime is going to be e to the x minus cosine x. And h double prime is going to be negative cosine of x. Oops. Don't mind that, my bad. And so, just cleaning this up. If we plug in x equals 0 and we use these formulas for the derivative here, what we're going to find is that c1, we'll plug in 0 here, we get 2, plus c2, and then 1 minus 1 is 0, so this is 0, and then c3 is going to be negative 1. And this says the same thing as 2c1 minus c3 is equal to 0. So now we go over here, and let me make a new page. My bad. Current templates. Move you over here. Okay. So now we're here, and the equations we had were, let me remind us, 2c2 plus C3 is equal to 0. C1 plus C2 is equal to 0. And then finally, 2C1 minus C3 is equal to 0. So now let's attempt to solve for this system. Okay. So first thing I notice is, and let me label these equations 1, 2, and 3, is I can cancel out the C3s by adding 3 to 1. So then the new equation becomes 2C2 plus C3 plus 2C1 minus C3 equals 0. And we still have our other two equations right here. But what's nice, okay, so, and you know what? Let me actually erase these and bring them back in just a bit. Let me focus on this first equation first. So the C3s cancel, and if we factor out the 2, we get 2C1 plus C2e is equal to 0. And dividing out the 2, we get C1 plus C2 equals 0. But we can see that this is already one of the equations that we have. And so what we see is that when we've added 3 to 1, we didn't get an independent equation, as it's called. So now we know one is, or let me rephrase. Now we know does not yield any new information about our solutions. Since this equation that we got is already in our system. So now we just have to worry about solving these two equations here. How do we solve these? Well, we can put it such that we can express both C2 and C3 in terms of C1. So notice that equation 2 rearranges as C2 equals negative C1 and C3 equals 2C1. So what this tells me is that, notice how there's nothing constraining C1. So if I plug in anything for C1, I'm going to get corresponding values for C2 and C3. Therefore, our solution family for this linear system it has like 1 degree of freedom obtained by controlling C1. And so here, to make this more explicit, if we set C1 to be T, the solution family of tuples is given by T, negative T, and then 2T. So now to find a particular linear combination for our functions, we just depict some convenient value of T. Let me write this out. Of f, g, h, choose some value for t. Value for t. Here I will choose t is equal to 1 since it's the easiest. That is not 0. And it's important here that we pick something that makes not all of these 3 coefficients equal to 0 at the same time. Because our goal, now that we think this might be linearly dependent, if it were linearly independent, we would be able to solve for C1, C2, and C3 all at once and find that they all must be 0. But now here we know that, in fact, we have a degree of freedom for our solutions. And so this tells us that there's linear dependence now. And so to get a linear combination, a non-trivial one, I'm going to choose something that makes it such that my 3 coefficients are not all 0. t equals 1 works to this end because this gives us c1 is equal to 1, c2 equals -1, and c3 equals 2. And so a non-trivial linear combination is then f of x minus g of x plus 2h of x. And by what we just did, we know that this has to be 0 for all x. Very nice. For the next problem, it's the exact same setup. So again, our setup, we're going to set c1x plus c2x squared plus c3x to the 4 equal to 0. And this has to hold for all x. Okay. Now, one thing we could do, and this is perfectly okay, is to just copy what we did in the previous problem, where we used derivatives to get our 3 different equations. So we got this one, we took a derivative, we got this one, and then we took another derivative, and we got the third one right here. But I'm going to introduce to you guys another way to think about this specific problem, because all of these are polynomials, and this is going to be like useful for like an observation. So notice first that the left side is a degree 4 polynomial. Right? Highest term is 4. Or I guess to be more precise, it is a polynomial of degree at most 4. It doesn't have to equal 4 because, for example, c3 could be 0, in which case our polynomial is just quadratic. Or, for example, c3 and c2 are both 0, in which case our polynomial is just a linear function. But we know the polynomial has degree at most 4. Therefore, the equation c1x plus c2x squared plus c3x to the 4 equals 0 has at most 4 solutions, right? This has at most 4 solutions. This is just the case for any polynomial. The roots could be real or complex, but the point is that including complex solutions, we're going to have at most 4 different numbers. And here, actually, let me clarify where we're considering the linear independence. So here, the domains of these functions are the set of all real numbers. So for them to be linearly independent, our setup over here, we need to see whether we can find c1, c2, and c3 such that this holds for all numbers x in the domain of all 3 functions. In this case, the set of all reals. And this is where it gets important. When we write this, so let me write that whole thing star as star. Notice that star says that every number x in R, and I forgot to write, has at most 4 solutions x. But star says that every x in R is a solution to c1x plus c2x squared plus c3x to the 4. In particular, it has infinitely many solutions. In particular, our polynomial has infinitely many roots. But the only polynomial that can have infinitely many roots is the polynomial that's just 0. All of its coefficients are 0. The only polynomial that can have infinitely many roots is the 0 polynomial. In other words, the constant function 0. Therefore, it must be the case that each of these coefficients is 0. And thus, our functions are linearly independent. This is a nice trick to know, because notice how it avoids having to solve the system that we had to solve in the previous exercise. The only caveat to this trick is that it only works if you're given 3 functions that are all polynomials. In this case, where we're given the polynomials x squared, and x to the 4th, and so this logic carries out. For the previous example, we wouldn't be able to do this because here we weren't given polynomials. We were given like e to the x minus cosine x, e to the x plus cosine x, and then cosine x. All right, that's it for this video. If there are any questions, please feel free to leave a comment. Otherwise, I'll see you all in the next video.